So Metaspin. So we started 2023. So we're 8 partners. So some of these partners are here. So we have Melika, we have Damien, Daphne. So we're very excited to work towards metaplastic electronic devices. So a lot has been said already in this direction. So it's really all based on this work from Damien's group. So it has already been introduced to this audience today. So and around the concept of catastrophic forgetting, which I will not repeat. So then simply, when this is an issue in neural networks, so then every time you want to learn a new task, you forget the previous ones. It's a huge issue. And then in his work, he could show that in binary neural networks, this could be significantly mitigated by the use of hidden states in this binary synaptic neural networks. So we asked ourselves if there was something that we could do from the hardware point of view to realize this type of synaptic elements. So then in principle, we'd like to have a system that has binary states and also analog states within each of these binary states. So then it seemed ideal to us to think about putting together magnetism and ionics. So then we know that magnetism is very good at providing binary memories. And from the other side, we all know membristors that can do all these different analog states. So, and this is really the core of the concept of magneto-ionics, which is something that it's been out there for a while. So then in this context, that means that we're going to get the 2 binary states from magnetism, and we're going to get a number of, let's say, these hidden states from the ionic control of magnetic properties. So then that means that each one of these states could be biased with ionics, and then for that to be easier or harder to go from one to the other. So I will go in a little bit more detail now regarding what this means and what the mechanisms are. But this is really the core idea of Magneto-spin. And we really have a wide variety of activities in the project. We're going from materials to devices to algorithm design, and really with a good communication between algorithms and devices in particular, because we need them to adapt to each other. So this is really the work that we're doing in this project at the moment. So then I cannot show you this yet, but I hope I can show you some interesting things that we've been doing, in particular on the magneto-ionics side. So so let me tell you a little bit more about how this works. So if we have a magnetic system like this one, so cobalt iron boron is really the archetypical magnetic material for the magnetic recording industry. So we're really going directly to a material that is relevant from the technological point of view. So all these materials are here typically 1 nanometer or less in thickness. So we're really talking about nanostructures. All the magnetic properties here mostly come from the interfaces. So what happens here is that we can interface this magnetic material with hafnium oxide, which on the other side is a very good material for membristors. We know we have a very high ion mobility in these systems. So if we put, well, this is one particular case of a device where we have an ionic liquid to apply an electric field, but you can really forget for the moment about that. So you only need to see that we have 1 electrode here, which is our cobalt iron boron, and a top electrode, and then we can apply an electric field across this capacitor. And what's happening is that the ions in the hafnium oxide are going to move towards the magnetic material or away from it, and they're going to change significantly the magnetic properties. And this is what we're counting on to create this hidden states in the magnetic binary state. So here what we see is this is an anomalous Hall effect measurement. So this is a magnetotransport technique in which we're sensitive to the spins in the outer plane direction with respect to the surface of the sample. So then that means that when the spins are pointing out of the film, we get the maximum signal, and then when they're pointing in the plane of the sample, we don't get any more signal. So this is what you get in the as-grown film. So the as-grown doesn't show any signal. And then as we apply negative voltages to the top electrode, that means anything that is negatively charged, so most likely containing oxygen ions, will move towards the interface with the cobalt and iron. So progressively, we are picking up now a signal from this device. So that means that the spins are progressively going from in plane progressively to the out of direction. Then here you can see that we can really get a nice hysteresis loop, which is what you expect from a magnetic system. So then you have these two binary states for magnetism here and here, because we're sweeping the magnetic field. So what we learned from this is, well, this is actually very well known from the material side. So then this is, if you take one of these films and then you just oxidize it in a sputtering chamber, then you could really get this type of changes in what we call magnetic anisotropy. So then the actions in space along which the spins want to align, so out of plane or in plane. This is well known from materials, but then this is a dynamic way. It becomes here a feature of the device. So, and yeah, well, this can be even a little bit more complex. So then you can go all the way up to getting your full signal, but you also have to be careful, because if you do it a little bit fast, which is, I mean, this is another sample where we start from the as grown, and then you do this a little bit faster, then you can go past the perpendicular anisotropy, so this nice hysteresis loop, and then end up without signal again, because if you don't have enough oxygen at the interface, your spins will be in plane. But if you have too much, they will also be in plane. So then there is this narrow window in which you can get the spins to point out of the plane. And this is what we explore to create this kind of analog degree of freedom in magnetism. So all these intermediate states for the spins. And of course, that since this is related to oxidation, these states are non-volatile. So, and this is what I want to show you here, so that we wanted to make sure that this was really related to oxidation at the interface, because we have here cobalt and iron. So if oxygen is interacting at the interface, we expect oxidation. So we went to the synchrotron, and then we could see by X-ray absorption spectroscopy that this was really the case. So then here we see the signals from these samples that we're looking at here. And we can really see signature of oxidation as we do more and more gating of these devices. So this we can really confirm that is an oxidation-related effect. So we're oxidizing and reducing the iron and cobalt here at the interface of the cobalt-iron boron. And this is modifying strongly the magnetic properties in a non-volatile way. And we can do this step by step, and then have a lot of intermediate states between the maximum and the minimum effect that we can get. So keeping this in mind, then we go now to a device design that is a little bit more what you're used to seeing. So then there's the whole bar structure, completely solid state. So we forget about this ionic liquid that I showed you before. So once again, we're measuring the anomalous Hall effect, same signal as I showed you before. Only here we're looking at half of the hysteresis loop to make it easier to visualize. So what we're doing here is we're pulsing the voltage at the gate. So we're applying pulses of 750 milliseconds. And then once again, this is the +1 -1 states from magnetism that you can get with the magnetic field. You can go from one to the other. But then as we go, we apply this gate voltage, we can see that how the signal is being distorted by this voltage. And what we can do is, if we draw a vertical line here, we can follow this change, and is actually what you're looking at here. And then is a completely reversible process. So then we can generate all these intermediate states in one direction, and then we can have them in the opposite direction with the opposite voltage. So, so that's really looks a lot like a memristive type of response. But the difference here is that this is a magneto transport measurement. So it's a magnetic signal. We pick it up electrically, but it has magnetic information in it. So that is the big difference with the memristor, where we are only looking at the effects of ionics. So then we thought, well, what can we do with the magnetism from this device? So we cannot do in membristors because they're not magnetic. Can we do more than just potentiation and depression? So So this is what we wanted to look at. And this is what happens. It's a single cycle of what I showed you before. But then this is done a different external magnetic field. So we start with the purple one here, which is done at very low magnetic fields. And then if we redo the experiment with much higher magnetic fields, then we see that the profile of this curve is changing. So then if we want to see this as a synaptic element, so this will be our weight update profile. And we can see we can change the linearity of the weight update profile with an external signal. So we found this very interesting because, I mean, we know from the membristors community that actually getting a linear weight update profile is, it can be a little bit tricky. So then there are different strategies to do this. So then either programming it in a certain way or simply by material science approaches, like, for example, doping. So, but once again, like I said at the beginning with the magnetic materials, so we can do a lot of things from the material science point of view. But here, this is a feature of the device. We can switch it on and off. We can change dynamically between an exponential type of profile to a linear type of profile. And this, in principle, well, as you always well know, a linear weight update will make learning for synapses a lot more efficient. So then by using this functionality, we could in principle control how well a group of synapses can learn under a magnetic field. So, and this is reminiscent of what neuromodulators can do in the brain, in biological systems. So this is an added value to the synaptic elements that comes from the fact that they are magnetic. So, yeah, so this, from the point of view of magnetism, so why would this signal change in this way? So that is because we have two components that are competing against each other. So we have, on the one hand, this pulsing of the gate that is making the spins align from this direction to this direction. But at the same time, if we apply an external magnetic field, if the magnetic field is high enough, the spins will always align with the magnetic field. So if the magnetic field is pointing up, and we have a competition between the effects of the gate, wanting the spins to go in plane, and the magnetic field pushing them out. So then in an intermediate competition between these two components, then we can find these interesting effects that we see here. So it's really a competition between the effects on magnetic anisotropy and the strength of the magnetic field. Yeah, so then what about retention? So then what we see here is one of these potentiation depression cycles that I showed you before, where we waited for a couple of hours to see how stable these states are. And we could find that, well, first of all, the potentiation and the depression are not quite the same in terms of retention. And that is because we're dealing with oxidation and reduction. So the end product that we get is not the same in both cases. So here we're generating an oxide, which is pretty stable in air after we switch off the gate, while here we're taking away the oxygen from an oxide and turning it back into a metal. So that's not very stable at the end of the process. So then here it remains, well, at the beginning we have a spike, which we think is most likely related to charge effects, that they vanish very fast. And then we have a relaxation that finally stabilizes in a well-defined state. Well, when we do the potentiation, this doesn't really seem to saturate very easily. So then this is the part where we think that oxygen is probably creeping back into the system after we take it out with the voltage. And because we're doing all this in the air. So then we see that because of what we're doing, so we're not just moving ions up and down, we're really oxidizing and reducing. These are not symmetrical effects. So then ideally, we would like to work with this branch of this curve. So then we talked to our colleagues, Damian and Kellyanne, And then we could, together with them, so then we figured out that we could be working with a system like this. So if we want to really take this to simulation level and see what a neural network could do with this type of synaptic elements, then we have to figure out a way to make this the more realistic system we could make. So then here, if we think that one single synaptic element is composed of two devices that are being subtracted, so the whole voltage from one, actually the total whole voltage is the subtraction between the whole voltages of these two devices, then we could work with only the branch that is very stable. So yeah, so then using this system, which, by the way, we now made into a real device, and this is the poster that Himadri, postdoc in our group, is presenting later on. So using this model and the actual data from the devices, they could make this nice simulation on this neural network simulation where they tested the MNIST data set, and then they could find that indeed, when the network is trained under with a field of 5 millitesla, so the accuracy is much lower than when the training is done at higher magnetic fields, simply because now at high magnetic field, the weight profile is linear compared to a weight profile that is exponential. So, so once again, this gives another degree of freedom for tuning how a network can learn, how groups of synapses can learn with an external signal that could be applied to the network. So, well, let me tell you in this last part of the talk a little bit more about the mechanisms for magneto-ionics. So, what I showed you before was a device that was in the hundreds of nanometers. So we wanted to learn a little bit more about how this transition between the spins being out of plane and in plane actually happens. So then we can get here the anomalous Hall effect signal, which is the same as I showed you before, this kind of memristive-like response with positive and negative voltages. So once again, we go from the full amplitude to the smallest, to fully quenching the signal and back and forth, because spins are following a different direction according to how many gate pulses we apply to the gate. But then we went here to much bigger devices. So you see this is 40 microns, so it's really big. It really behaves in the same way in terms of electrical signal. But we wanted to do microscopy. So this is magnetic imaging. So what you see here in the initial state, so there's two colors, they mean spin up and spin down. So then they're all aligned in the vertical direction. So they, the whole system has perpendicular magnetic anisotropy, but we have the two spin states here that are present. So these two different colors. So what happens when we apply a gate voltage and then we follow it over time? So then we see that we start getting an effect at the edges of the gate electrode, and then this progressively moves towards the inner part of the gate electrode, and it's kind of erasing this what we call magnetic domains. So this is really the component of the spins that are in the plane of the sample. So this was to us quite a surprise, because when you look at this, you could imagine that all the spins are collectively turning towards the in-plane direction. However, we see here that this is not a homogeneous transition. So we actually have more or less a nucleation of the in-plane state of the spins that are like this. And then we really have a defined boundary between the spins that are pointing in this direction and the spins that are pointing in this direction. And then this boundary is moving under the application of a gate voltage. And this is a reversible process. So then after we do this, then we change the polarity of the gate voltage, and then this expands again towards the edges. So yeah, so then this was really something new to us, to see that this was not necessarily a homogeneous process. So well, this is what it looks like in dynamics. So then you can really see it moving in and out when we change the polarity of the gate voltage. And this is very interesting, not only just to learn a bit more about the process, but also to see that this, what we call the spin orientation transition, which is this boundary between the two anisotropy states, is actually mobile magnetic structure. So just like you could think of skyrmions or magnetic domain walls. But in the case of skyrmions and magnetic domain walls, you're going to need a magnetic field or an electrical current to make them move across a track. Well, here we're using voltage. So this makes this extremely interesting for spintronic devices where we want to use less energy, because here we're only using a voltage and we're only using, let's say, the leakage current from the gate, so which can be a lot less than in spin torque devices. So yeah, so once again, so this is here the difference. So if you have a magnetic domain wall, you have a spin up and spin down at the two sides of the domain wall, where here you have actually two anisotropy states at each of the sides. But what we want to have, if we want to use this in any way, is we would like to have, like domain walls or skyrmions, possibility to nucleate it in a specific place and then to have a unidirectional propagation across a track, and not really the circular kind of motion that we see here. So we wanted to have a look at that and see if it was possible. So then we knew that in this system to have relatively low magnetic anisotropy, we could, even by depositing a gold electrode, we could locally modify the magnetic anisotropy. So since this effects are related to changes in the magnetic anisotropy, we said, well, maybe, what we want in the end, if this is our device, is that we can have a nucleation in one of these corners and nucleate here and then have it propagate in the other direction. So if we put this type of variation close to one of the edges of the gate, then we could have a shot at when we apply the voltage to actually nucleate here and not anywhere else, and then just have it from there and then move it up and down the track. So this is what really what we managed to do. So then you see it here in the track. So then the white part is what's under the gate, and it's the part that has perpendicular anisotropy. And then as we apply pulses to the gate, you can see it moving to the left until the whole state is finally in the in-plane direction. And this is a reversible process. So then once it arrives on the other side, then you can push it with positive voltages from the left to the right. And what is nice is that you can track the motion of this object along the track. So what you see here are these numbers really correspond to the images that you see here, so that we can really get an electrical readout of every position of this spin rotation transition along the track, and then you can get the electrical signal that I showed you before. So then we finally understand that this electrical signal can actually be due to an object moving across the track and not necessarily to spins collectively moving. So then we know that magnetic information carriers in spintronic devices have enormous potential for neuromorphic computing. Especially, we've seen great work with skyrmions recently. So we think that knowing now that we have this new information carrier that is driven by voltage could really help us to design new devices for neuromorphic computing. And then we're really looking into this at the moment and see if we can use this to better design our synaptic elements. So yeah, I think I should be at the end of my talk now. Yes. So, well, I hope I could show you that magneto-ionics has potential for the design of synaptic elements. So we're really convinced that the fact that we're putting together magnetism and ionics brings an added value to the already well-known things that ionics can do. I didn't show you a lot of different systems today, but it can be applied to a whole different types of magnetic materials. And in particular, I think we have a lot to learn from the memristors community, and there's a lot of interactions that should come from talking between the spintronics and the memristor community. And yeah, and then we think that the magnetic degree of freedom can bring a lot of new things. And recently, yeah, the fact that we could, by using ionics, we could see a new type of magnetic information carrier that is driven by voltage. And we're excited to work with this for new types of spintronics neuromorphic components. So Let me thank everyone that's involved. I mean, our collaborators from Metaspin, but also from other projects as well, because I mean, there's a lot of work also before Metaspin that led to this. So then everyone's involved, and in particular to the students and postdocs working in our group. So most of the things that I showed today were done by Guillaume Bernard, PhD student from Metaspin, and Damien Kerlios and Kelian from the neuromorphic algorithm side. And and I would like to thank you for listening.
Thank you very much for the nice talk. I had a materials-related question. I was just wondering what was the motivation behind the choice of ITO as the top electrode and how it reacts with the material.
Yeah, we're actually the beginning was very simple. We wanted to be transparent so we could do microscopy, so the kind of things that I showed today. So it's a compromise between conductivity and transparency. So then it's relatively conductive, so we can be an electrical contact, and is decently transparent so that we can see the domains through it. So sometimes we have to watch out because sometimes the contrast is inverted or some strange optical effect, but we can see very well through it. Now, the interesting things that I showed at the end with the edges of the electrode, we think are related to the fact that we have ITO, because ITO is an ionic material itself. So then we did the same experiments with platinum electrodes, and we don't get this type of behavior, this nucleation at the edges. It only happens when we have ITO. So it is a very interesting question. We started with just, whatever, transparent, and now it's kind of a feature. Yeah.
Thank you very much.
Quick question on the algo side. You had a slide where I think you used the word simulated learning, where you showed some results for MNIST. I don't think I fully understand what you mean by simulated. Does that mean it's not a device in the loop, it's a simulation-based result? Purely?
I mean, the experts are here, but I will try to answer the question, and they might just want to add something to that. So the physics of the devices were used to conduct this simulations.
Oh, cool. So does that mean that in the simulation, the experts used some level of mismatch of the components? That was you obtained post-characterization of a device, or is this an estimation of how much mismatch you get in the device?
Well, actually, the actual data from the devices was used. We also introduced the noise from the device. We really try to bring as much information as possible from the devices. Yeah. So they really work with the actual data from the devices. Yeah.
Thank you very much. I will complete with a question on the physics. Have you tried to extract critical exponent for the motion of the domain wall using the gate? And did you compare them to what happens with the current-driven motion or field-driven motion?
What you mean for the motion of the SRT? Yeah, we did do. Well, I don't think I have it in the backup slides. Probably not. Okay, but we did do velocity measurements with different amplitudes of the gate voltage, and we have an exponential law. We think that it looks like creep, but the difference here is that we cannot assume that we have a one-dimensional interface into a 2D medium, because this object is very wide compared to the pickup lines that we have. Is comparable to the width of the hole bars, which is how we measure. So I think that we have a mixture between the of this SRT and also its internal structure, that we're also measuring its internal structure, which you don't consider when you look at creep dynamics and you say, oh, it's exponential, you can get an exponent out of your law. So then we're still thinking about that. So it looks somehow far from linear, but yeah, we have to think about what this exponent could mean. Yeah.
Hey, Liza, thanks for a really great talk. I was quite taken by the change in the gradient you showed of where you applied the different magnetic fields. You had that kind of like green to purple curves. Yeah, this one. So basically, once you have like a relatively high enough field, you really flatten it down. So there's two quick things. One of them is if you had some local way to apply a field controllably, do you think you could use it as a kind of field-based inhibition thing?
Yeah, we think that that could be a feature. Yeah, I mean, one thing would be, yeah, I mean, if you have some strip lines where you can generate some local Ørsted fields, and then, yeah, the next level, which is something that people are starting to do, is like there is in the literature already magneto-ionic control of exchange bias, for example. So this could be a way of controlling this at the single device level, for example.
Yeah, it seems super neat. You can basically freeze out to some extent the activity of certain regions. Yeah, really, really cool. Thanks again.
Thank you.